Oh, there's more here. Okay. All right, so this is the last of these lectures, so hopefully I get everything done I wanted to do. I think we'll be fine. So yesterday we talked about the, well, I talked about, and you listened, about the Schwarzschild space-time. And I mean, one of the main reasons for giving this example was that I think that in terms of all these various ideas in this 3+1 decomposition, and just considering how the dynamics of the space-time and of the coordinates can work, I think that the Schwarzschild producer is a very nice example, because on the one hand you have a solution, you can just write down the Schwarzschild metric and you know that it's time independent and it's a stationary solution, it's this black hole, you know exactly what's going on. I mean, it's not that often in numerical relativity or in general relativity where you have so much knowledge about your solution, okay? And so there you can then do these things where you start playing with the coordinates, and all of the things I talked about yesterday, essentially all these wormholes and trumpets and going from one to the other, this is all just changing the coordinates, right? And in a sense choosing coordinates which are optimal for a numerical computation. And in doing these kind of calculations, so in doing black hole simulations, one of the main problems has been choosing appropriate gauge conditions so that you can describe these black holes on your computational grid and get reasonable results, and that all of your coordinates don't suddenly disappear inside the black hole and all kinds of crazy things happen. And in some sense, actually, black holes are, in a way, an easy case because they're very compact and they actually don't do very much. I mean, they may move around, but the black hole itself doesn't change very much over time. It has a certain mass, it has a certain spin. It doesn't do crazy things. If you start thinking of these like critical collapse of vacuum wave solutions, like Brill waves, you have these things over a much larger scale, and they go through these very intense oscillations and perhaps collapse to a black hole and perhaps not, and it's much more difficult to actually capture the essential physics. Anyway, enough of that. So just to finish off, some comments about the Schwarzschild evolutions. So these results that I showed at the end, I had talked in the lecture about maximal slicing and what happens with maximal slicing, and gave this solution which originally came from this Estabrook paper for these cylindrical slices. In modern evolutions, we don't use maximal slicing because it's an expensive elliptic condition. What we use instead, in general, is this 1+ log slicing. And I know Thomas talked about this, but I just want to mention a few things about 1+ log slicing in the context of these Schwarzschild evolutions. So, let's take a and by slicing condition, I mean lapse. Right? You shouldn't be overwhelmed by these terms. I mean, when people talk about the gauge conditions, it sounds very, very complex, right? It conjures up field theory and all kinds of abstract things going on. Gauge conditions are just coordinate conditions. They're the conditions that decide for you what the coordinates are. So in a sense, it's somewhat that they're mundane. Right? They're not actually that fancy. So for a condition for the lapse, the 1+ log condition is usually written as this. We can also write it. The variance of it, I think the one that you did an exercise on in Thomas's lectures was a variant without the shift term. So if we consider so we consider the non-shift, a different version. Okay, this version here, in is some constant that we choose. It's normally chosen to be 2 for essentially historical reasons, but I'm just leaving it as in here. If we consider this version and a stationary state, okay, so we perform some evolution. Say we start with this wormhole data, which are maximally sliced, right? The initial data have trace k as 0, and we start evolving, the coordinates will change, things will happen. If we start with a lapse equals 1, we know things are going to change, and the system will evolve. If it's going to eventually settle down to something stationary, where there is no more, by stationary I just mean in very practical sense that the data in your code don't change very much from one time step to another, and you can essentially stop because you're not going to learn anything new. That's what I mean by stationary. If that happens, then we must have that the time derivative of alpha is 0 if it's stationary, and that would mean the only way we can have this 0 everywhere is either the lapse is 0 everywhere, which would be a bit unfortunate, or the trace k is 0. Okay, so this slicing condition asymptotes. If it settles down to anything, it'll settle down to maximal slicing. Okay, so this. Okay, so if you want to do maximal slicing, you can, but then you have to solve an elliptic equation, and this is expensive. You can instead use this thing, which is now you have an evolutional equation for the lapse, and you know that if this thing gets to some final state, you'll have maximal slicing anyway. So this has a similar behavior to maximal slicing, but is easier to implement. And this is very, very large. Then of course you'll need k to be small. So So this is another way of getting maximal slicing. And if we look at the value, for each of these values of n, we will have a different version of this trumpet solution. Okay, so the what did I call this surface? This I don't know, trumpet surface, the cylindrical surface. So the value of the cylindrical sorry? Oh, sorry, that's 9. Yeah. Sorry, yeah. Sorry, yes. So the value of the location of this limiting surface will depend on your choice of n, and so if you plot this, then plot R naught, it will asymptote. So I should put the R naught over here. We'll go to 3m over 2 for very large R, very large n, and then it'll come down to 0 for very small n. So as n goes to 0, then this limiting surface gets closer and closer to the singularity. So you certainly don't want to use just obviously dt equals 0, dt alpha equals 0 is not a very interesting choice of lapse condition. That's that's geodesic slicing, right? If you start with lapse equal 1 and you just say I don't want the lapse to change, I now have geodesic slicing, and we end up in the singularity. So that's consistent. That as n goes towards 0, you go towards the singularity. And usually for historical reasons, I say we use a value of 2. And for this, it's something like 1.31 m. Okay. So if you read, I don't know, for some reason read some papers about black hole evolutions, and someone talks about a surface some 1.31 m, this is because they are using the standard choices for maximal slices. The other thing to mention about the 1 plus log slices is that you saw this yesterday in these pictures I showed, these images, that in maximal slicing, this surface 3m over 2 acts as a barrier to the slices. So the slices will, in the Penrose diagram, the slices will rise up and then they'll hug around this surface, but they won't pass through it. In 1 plus log slicing, there is no barrier, and the slices can actually go through this surface. They will asymptote to stationary slices which end on that surface, but they can, in the meantime, pass through. And this was where I had this picture. I think this is the last Penrose diagram of the course. Right? Right. So I think if we just exaggerate what the surface looks like, the slices go up. I think well, these ones were they maybe went up, and they went past the surface, and then later they were over here. So they can actually go into the surface, and then they get moved back out again by the shift vector. Now the shift, I haven't talked about the shift condition. The shift condition, we usually use the shift condition called gamma driver shift condition, and I'm not going to write it down because it's completely non-illuminating. It doesn't tell you anything. There is basically no physical or geometrical or mathematical intuition you'll get from seeing this shift equation. Okay. The only thing to say about it is the origin of the shift, this gamma driver shift, is minimal distortion. What was called the minimal distortion equation, which was again an elliptic equation, and then this was again turned into some analog evolution equation, like was done with the lab. So just to mention that the okay, and the minimal distortion condition, I'm not going to go into any detail about that, but that particular condition essentially does what the name suggests. It tries to remove large gradients essentially in your metric components. So if you don't have a shift, right, the slices move up like this, and the lapse collapses, and then this collapsed region grows, like I showed yesterday, and where that's happening, the metric is essentially getting bigger and bigger, and it's getting sharper and sharper features, and the minimal distortion condition acts against that to smooth things back out. And so the idea of this shift condition is to produce a solution which doesn't have these grid stretching features in, if you like. And so that's what motivated the shift condition, which then leads to these slices which do this. Yeah. I mean, the other reason for not saying so much more about it is that in some sense, this was done without understanding what was going to happen. Right? So the people thought that this minimal distortion condition was good. They turned it into an evolution equation because this was a vector elliptic equation, so it's even more painful than what happens with maximal slicing. And then you use that, and then a few years later, when you fixed other problems, you find that all these other things happen. But this was not done by design. It just turned out to work that way, which is very, very fortunate. Okay, so that's all I wanted to say about these Schwarzschild evolutions. Does anyone have any comments, questions, issues? Okay, all right. So now let's move on to more general black hole initial data. There are many ways to produce black hole initial data, and I'm only talking about the one I'm talking about is sort of most closely connected with all the other things that we've discussed. And it is also a very, very common method, but certainly not the only one, so I don't want to give you that impression. So now if we start with if we go back to the beginning, we start with the Einstein equations, and we do a 3+1 decomposition, right? We have then, so let's take our back. Okay, we have data right? These are our spatial data, and given some choice of lapse and shift, we can now evolve these data to the next slice. Okay, and then we can write down the constraint equations that these must satisfy. But the problem is that the constraint equations, these are 12 quantities. Okay, so this is right. These are symmetric tensors with 3 indices, so they each have 6 components. So this is 12 quantities. Okay, we have only 4 constraint equations. Okay, so we have 8 quantities that are undetermined. Okay, and if you look at the constraint equations in their basic form, it's completely unclear which are the 4 quantities that are being constrained and which are the 8 which are free. Okay, so the idea of doing these conformal decompositions is to separate out the constrained, the freely specifiable quantities and the constrained quantities. The A Okay, so if we make this, we can make the standard conformal decomposition. This changes the Hamiltonian constraint to this Lishnerovich equation for the conformal factor, which we've seen again and again. And then you also have to make some decomposition of the extrinsic curvature. So one decomposition, I mean, for our purposes, they're all somewhat equivalent. For one decomposition, which one shall I pick? I'll pick the conformal thin sandwich decomposition because that's my favorite. Okay, and in this particular decomposition, right, you specify the conformal metric, you specify the time derivative of the conformal metric on your slice, and you specify trace k. Right. And then you solve the constraints. You solve the Hamiltonian constraint for the conformal factor, and the momentum constraint. The nice thing about this particular decomposition is that the momentum constraint is now a vector constraint for something which can be interpreted as the shift vector. Okay. This doesn't actually have to be the shift vector you use in an evolution, because you're talking about initial data here. But this particular vector then allows you to construct the data. So now you have that gamma ij's. You reconstruct your physical data this way. The extrinsic curvature actually you have to choose this guy as well. Actually, well, let's say LB. No, this is more complicated. Anyway, I won't mention that. Okay. Yes. Yeah.
We have 2 unknowns, gamma ij and k ij, in the decomposition part.
Here, sorry?
The upper.
Yes.
So instead of using k ij, we can use a definition of the k ij as minus half the derivative of gamma ij.
Minus a half. Well, in the definition of the definition of, well, this is the definition of Kij is
minus half the derivative of normal
right.
gamma ij.
Right, but that ends up being, so if you rewrite, you could rewrite this essentially in this way, that you have this operator. I'm not going to describe the operator, it doesn't really matter for these purposes. This is basically a differential operator on the shift, and then this is the time derivative of it. So the derivatives of the shift enter into the definition of the extrinsic curvature. right? So you need this quantity as well. Yeah. Okay. So you end up with this. You have to specify this as well. I didn't want. Maybe I shouldn't have done the thin sandwich decomposition because this complicates things somewhat. But anyway, you can see that this is a piece of data that you've specified. You actually specified this one as well. This is some extra. And then for your shift that you got from solving the momentum constraint, you've got this guy. And so then your extrinsic curvature is then what have I done? That doesn't look right, does it? Oh, sorry, that's right. So you essentially get this. Is that right? Have I got the right power there? I think so. Okay, anyway, once you've solved, so this is the general setup, and if you look at the counting of this, you have now gamma ij has 5 free quantities, okay, which is essentially 6 minus 1, right? Gamma ij looks like it has 6 quantities, but you've actually pulled out the determinant in this construction, and so you actually only have 5. It turns out that delta time derivative of gamma ij is trace-free in the construction of this decomposition, and also transverse. I'm not sure if Thomas went through what transverse is, but a transverse vector is one for which gamma I. This is the transverse vector, and so this gives you 3 conditions. So you've got 3 conditions here, and another condition that is trace-free, and so this is only actually 2 free quantities. And then you have your trace k that you specify. That's another 1. Okay, so you've got 5, 7, 8 quantities that are freely specifiable, and you've got 4 constraint equations, and so you're done. And so you know that, so everything adds up. Okay, so there's essentially 8 numbers that you get to specify. Okay, and your choice for these numbers will influence the physics, of course, of your solution. But you can choose anything you want, and then see what comes out. Okay. So then in Thomas's lectures, I know he talked about the Bowen-York solution. So there's one particular solution where if you choose this is from 1980, actually. So if you look up Bowen and York, 1980, you'll find their paper. So what they did was, so there you say that it's, as our favorite assumption, it's conformally flat. This 0, so we could say it stays conformally flat. At least at the initial slice. Right? This is not some statement about the global solution. This is just on this slice. And trace k is 0. These are our conditions, and then we get the Bowen-York solution to the momentum constraint. So we get an analytic okay, and the great thing about this is that we can get a solution that represents either a spinning black hole or a boosted black hole. Okay, so we can get the extrinsic curvature consistent with a spinning black hole or a boosted black hole, and the great thing is that the momentum constraint, if you write it, once you've made these assumptions, is linear, okay? And is in some sense independent of the Hamiltonian constraint. So you can just solve the momentum constraint on its own, and since it's linear, you can add solutions. So you can also make a spinning boosted black hole if you want, because you just add the spinning parts and the boosted parts together, right? So the and of course, since it's linear, if you can do that, you can add together more and more of these things, and you can make multiple black holes. Okay, and this should, your eye should light up at this prospect, because one of the motivations for all of the work that we have talked about, motivation since the 70s, or since the 60s in fact, was to try and solve the two-body problem in general relativity, to understand the dynamics, the strong field dynamics of two black holes when they merge, right? When they come together and collide and merge and form a single black hole. And so to do that, you would need to solve the constraints for a system with two black holes, and now you're on the right track. You have a way of producing multiple black hole data. And in fact, you can produce 3 or 4 or 7,652 black holes if you wish. If you have the computer time to do it. Okay, so we have a solution to the momentum constraint that's analytic, and we're now left with the Hamiltonian constraint. And so, as usual, we end up with our favorite elliptic equation. Right? And then we must solve this thing. And for a boosted black hole, this term goes as 1 over r to the 4. And for a spinning goes as 1 over r to the 6th. Okay? All right. Now, and in each of these cases, if you just consider a single one of these, just a single boosted black hole or a single spinning black hole, this is an axisymmetric solution. So you can actually solve this in 2 dimensions. You don't have to produce some big 3D code to do this. Now, there's a problem here, which is this term blows up, right, at the origin. Now, you know that if it's a black hole, you expect that the conformal factor also blows up at the origin. And if you produce this wormhole-like data that we talked about yesterday for Schwarzschild, then we expect that the conformal factor blows up as 1 over r. Okay? And so if it blows up as 1 over r, this inverse 7th power of the conformal factor will go to 0 as r to the 7. Right? And so it will go to 0 faster than either of these terms. Okay? And so this equation actually will be regular at the origin. Right? Now that on its own is not enough to say, okay, good, everything's regular, away we go, because when you solve, you do not want to have to solve for the divergent part of this, this function. right? Because you essentially have something that's blowing up at the origin, and so then you say, what kind of boundary conditions do you put on? So in the past, right, you've always put on these boundary conditions and say, well, even though there may be a blowing up part of this, I am actually only interested in the part that doesn't blow up, and when I put boundary conditions at the origin that this function is 0 or has 0 derivative or it's otherwise well behaved. In this case, we know it has to blow up, so that's a problem. Okay. Now, originally, when people first solved this equation for this system, what they did was they said, well, okay, the origin is inside the black hole. I don't care about what goes on inside the black hole because whatever goes on inside the black hole stays in the black hole, right? Nothing gets out. So I don't have to solve the equation there. I don't need to produce data there. I don't need to do anything there because I don't care about it. I can actually excise the interior of the black hole from my simulation. And there's a whole class of simulations of binary black hole systems where they excise the interior. And so then you can say, okay, now I excise, so I don't have to deal with this r equals 0. But this then a consistent inner boundary condition for these equations. And you can do that, and you can produce solutions, but this is very, very complicated. Right? You then have to, you can produce, I guess the best way of doing this, the most successful way has been to actually produce a version of these equations, these solutions which are inversion symmetric as you go from one end of the wormhole through to the other, and then you can put symmetry boundary conditions at the throats of your wormholes, and you can make your inner boundary condition at these throats, and you can do this, but it's very, very complicated. Okay. What would make life much simpler, right, was if you knew what the 1 over r behavior was there. Because if you knew exactly what it was, then you could just say, okay, I know that part of the solution, and I just solve for the rest. And it turns out you can do exactly that. So you can write this solution as looking just like the Schwarzschild part of the solution plus a correction. So if we let psi, okay, we do this. This part of the solution is eliminated by the Laplacian operator, by the flat space Laplacian. Okay? And so if we make this choice, the Hamiltonian constraint becomes an elliptic operator only acting on u plus, well, we might as well keep this part the same. Okay, so now we have this equation, and this function is regular everywhere. Okay, and so you can go through and calculate that. Yeah, so now you've factored out the 1 over r part, and everything else that's left, it turns out, is completely regular. And so now you have something where the source term is well behaved over the entire computational domain. You expect the solution to be regular, and now you can, in some sense, naively go away and solve. And you don't have to worry about any inner boundary conditions. You don't have to do anything fancy. You can just solve it. And this was introduced by Brandt and Brugman in 1997. And this is called the puncture approach. And yes? I'm sorry? Oh, sorry. Yes. Right. That's a bit superfluous. Okay, yeah, so this is called the puncture approach. And the reason it's called the puncture approach is that in some mathematical sense you're considering the domain everywhere except at r equals 0. So you sort of punctured the domain. Okay. All right. And so this is a very, very easy system to solve in comparison to other ways of doing it. And as I say, I copied this technique in suggesting how to solve this Schwarzschild system yesterday. But the technique came first for this system here. And in fact, of course, it's very easy here because you don't have to work out the Laplacian of this other piece because it's just 0. So things become very simple. Okay. Okay, if we have made this solution, we're going to say, okay, what does this correction do to the solution? Okay, what happens to our space-time? Well, if we've added some, for example, some momentum to our black hole, right, okay, then we've probably added some energy to the system. And in fact, if you calculate the ADM energy of your space-time, okay, this can be turns out it can be calculated by a surface integral at infinity. If you calculate the surface integral of this this quantity in infinity, this will give you the ADM energy of the space-time. This comes from if you take the formula for the ADM energy and you make all of these conformal transformations and you make the appropriate limits as you go to outer infinity, you get this formula. And it's pretty clear that if you plug in this part, you just get m. Okay. So if if u goes as some k over r, or large R, right, which we expect because we've done this before. This is certainly what's going to happen. Then psi is 1 plus m plus k r as r goes to infinity, right? And this is some constant, right? Then if we plug this into here, we can now see that we'll find that if you just do the calculation, this is relatively straightforward, right? You just have to take the derivative of this with respect to r. This gives you 1 over r squared. This piece here has an r squared sine theta d theta d phi in it, so the r squareds cancel. Integrate the sine theta d theta d phi gives you 4 pi. There was another factor of 2 somewhere in there, and everything, pretty much everything cancels out, and you're just left with this piece. So you get m plus k, right? So what this u does, this correction function, is it indeed modifies the mass of the system. So you start with something, if you had 0 momentum or 0 spin, then these extrinsic curvature terms will be 0, and you just have Schwarzschild. As soon as you turn on the momentum, you turn on the spin, these terms appear. You then get this small correction u. This falls off with some power of r, and gives you then a little correction to the mass. So this adds to the mass of the your initial data. Okay. So one thing then that's very important to appreciate when you produce these kind of data is that now m is not the mass of the black hole. M is just a parameter. I mean, if it was Schwarzschild, it would be the mass. It's not Schwarzschild now. This is just some mass parameter. Obviously, increasing this or lowering this is going to increase or lower the mass. So it parameterizes the mass, but it is not the actual mass. The mass is this, okay? And that's important to understand. Okay. Another way of calculating the mass. Actually, what is the time? It's 1:15. Let's see what I want to talk about. That's fine. Yeah, I will. Let's have a break for a couple of minutes, and then I'll talk about another way to calculate the mass, and then give some more details about binary data. Okay. Okay. All right. So the another method of calculating the energy. Actually, if you want a reference on there was a couple of questions about where this came from and these ADM quantities. So the ADM energy is the total energy of the space-time. Okay. If you want to see where to get this from, what the full definition is of the ADM energy and how to get to here and all sorts of other interesting things about it, you can read. There's a paper by Amurahu and York from 1973. I can't remember the title. I think it's gravitation. I think we just said something like gravitational energy. Some very short title. But this paper talks in great detail about these things. And that's a very good reference for this. Okay, so another way of getting the mass, which I want to go through because it's instructive about the properties of these solutions, is that what we have here is we have a wormhole solution. Okay, this is it's just like Schwarzschild, but we've kind of modified it a little to give it some momentum. So it's again one of these wormholes, and it turns out that you can make an inversion transformation on these data, so that essentially, large R here is one end of the wormhole, and small r, right, is at the other end, is on the other side, and you can make an inversion transformation where you essentially define a new r as 1 over the other r, and it flips everything around. So you invert what was outside as what was on the top half of this picture goes to the bottom half, and vice versa. And it turns out that if you make this inversion transformation, okay, right, okay, we introduce some new r bar, some constant here, and some r bar, which makes this inversion transformation. This is like saying, right, you have your wormhole. Okay, this is right. This essentially points that are on one half of the wormhole get sent to the other half, and vice versa. This is just inverts everything around. If you make this transformation, it turns out that this form of the extrinsic curvature is not symmetric under an inversion. So with this extrinsic curvature, the top half is not equivalent to the bottom half as it was for Schwarzschild. Okay, so the Bowen-York extrinsic curvature solutions are not inversion symmetric. In this form. Okay. You can add additional solutions with higher powers of 1 over r, which actually will make them inversion symmetric. But as they are here, they're not inversion symmetric. And it turns out that if you take the boosted solution and you make an inversion transformation, right, then you get some new, I'll put a bar on it, which goes now as 1 over r to the 6, not 1 over r to the 4. Okay. Now, the fact that if you calculate instead of the ADM energy, the ADM linear momentum, it turns out that this 1 over r4 term is what gives you the linear momentum, just as the 1 over r6 term here gives you the boost. So sorry, the Aij goes as 1 over r4. Aij itself goes as 1 over r squared, right? It's because this is the square of it, right? So make that clearer. And for the spinning one, it goes as 1 over r cubed. Okay? So when you make the inversion transformation, the boosted one goes from being 1 over r squared to 1 over r. No, maybe that's 4. 4, I believe. I should check this. Yeah, and the spinning one becomes 1 over r cubed. Okay. Oops. Should put bars on these things. Okay, so.
The boosted one remains the same.
I'm sorry?
The boosted one remains the same?
No, the spinning one remains the same, right? The boosted one, this is just Aij, not Aij squared, right? So Aij goes from being 1 over r squared to 1 over r4 under an inversion transformation, okay? So the original one had some linear momentum, which came from the 1 over r squared term. The inversion transformed one, it goes only as 1 over r4, so there will be no linear momentum in this, okay? The spinning one, on the other hand, goes from 1 over r cubed to 1 over r cubed. So this stays the same. This has angular momentum in both halves of the wormhole. So what this means is that if I want to know the ADM, if I want to know the mass of the black hole, right, Not the ADM energy of the space-time, because the ADM energy of the space-time is going to the mass of the black hole plus any radiation that may be in there due to this boost or spin. If I go to this other half, I now have a version of the solution which falls off much more quickly, and so I expect that to have much less of an impact on the mass. And so if I calculate the mass on this other end, I'm probably going to get just the black hole mass, not the if I calculate the ADM energy at this other end, I'm not going to see any boost or any spin. I'm just going to see a black hole. No, I'm not going to see any radiation. That's the expectation anyway. That's the assumption that we make. Certainly we will see much less radiation because this thing is falling off much more quickly. So one way to get an estimate of the black hole mass is to go to the other asymptotically flat end, to make this inversion transformation and go to the other end and calculate the ADM energy there. Okay, so we've made a transformation of this. It turns out we can also make the appropriate inversion transformation for the conformal factor is that psi bar is A over R bar psi. Is the transformation of this, and you can see this if you just write out the line element. And if you write out these, and if you write this out, and then you make your inversion transformation on R, you'll see in order for this to be invariant, it must be invariant, then psi must transform this way. This will drop out. Okay. Okay. So now we write out. We now make the transformation on psi. We see that psi bar is going to be A over R bar, original psi. Okay, and now we include the transformation of R here to R bar. We will get A over R bar U, which is just these two pieces, plus A over R bar here, M over 2, which is that bit, and then R is, what is it? A squared over R bar. Right, so that cancels out, that cancels, and you get, yeah. This looks wrong. Is that right? Yeah, sorry, M over 2A. Okay, so you get this, all right? Now if we let this parameter in our inversion transformation equal M over 2, okay? We've just chosen to make this transformation, so we can make it however we wish. Now, psi bar becomes 1 okay. Now, I can take this, if I take the limit as R bar goes to infinity, R bar goes to infinity, R bar going to infinity is equivalent to little r, the regular R going to 0. Right? As R goes to 0, U is going to go to some constant. Right? U is this correction function. At the origin, it becomes some constant. Okay, it's a regular function. It turns out it doesn't become 0 at the origin. It becomes some constant. So then psi bar is 1 plus m over 2r 1 plus u naught, which is the right. That is the limit. I should say limit. Right, the limit as r bar goes to infinity of psi bar is exactly this. Or, well, I guess it goes to this, right? Okay, so it takes this form, and so now we see that we have something that falls off as 1 over r. We basically have an m over 2r form where our m, the piece on top is our original EM times 1 plus U naught. Okay, so you can see then that if we calculate the ADM energy at the other asymptotically flat end, we will get right? The ADM mass at the other asymptotically flat end is just the original mass times 1 plus U naught. Okay, and since we expect that at the other asymptotically flat end we're seeing the black hole without so much radiation in the space-time, then this is an estimate of our black hole mass. Okay, and it turns out that if you produce one of these solutions and you calculate this thing, which is trivial to calculate, right? This is you've produced U, you have this solution U in your numerical data, you just take your numerical data and you just read off this number, and then you have the black hole mass. Right? The other way of calculating the black hole mass is to locate the apparent horizon of the black hole and to work out the area of the apparent horizon and so on, and to get the mass that way. This is infinitely simpler to do. Okay? And it turns out that if you calculate the apparent horizon area and you work out the mass from it, it will agree with this extremely well, basically to arbitrary precision. For the boosted case, because in the boosted case, the other asymptotically flat end contains an extrinsic curvature which falls off extremely rapidly. Okay? For the spinning case, it doesn't work so well. In fact, for the spinning case, it's no use. Since you see that it transforms as from 1 over r cubed to 1 over r cubed, that the ADM energy you get at the other end is exactly the same ADM energy you got at the first end, and so you don't actually see only the black hole. What you instead see is the black hole plus some radiation, and which suggests that I should talk about radiation. Right, radiation. All right. So I'm going to reveal my prejudice about this radiation right from the beginning by calling it junk radiation. All right. This is what everyone calls it because it's trash. Right? We do not want to produce a black hole with some radiation. We just want to produce a black hole. Right? We want to produce we would like to produce a boosted Schwarzschild black hole, or a nice clean spinning Kerr black hole, or a nice clean spinning Kerr black hole that's also boosted. Right? And that's it. Okay? But we don't get that. Okay? Ask, if we consider that a spinning case, right, is a spinning is this spinning Bowen-York black hole a Kerr black hole? We know, or we have been told by our betters, right, that the only spinning unique black hole solution it's stationary and it sits there and it's just a black hole is Kerr. That's it. There is no other solution. This is a spinning black hole. So it must be Kerr. Well, no. It turns out that it's not Kerr. And we know that it cannot be Kerr because Kerr metric is not conformally flat. Right? The Schwarzschild metric was conformally flat, and we took that as our lead, and we produced these nice data which are also conformally flat because this makes life very simple. Right? If the background metric was not, the conformal metric was not flat, this Laplacian operator here will be the Laplacian with respect to some other metric, which means it will be horrible. Okay? So having chosen the flat metric, we have a nice flat place Laplacian, everything's great, we can produce our data. But it's not going to be Kerr because Kerr is not conformally flat. We've produced some other thing. Okay? Well, we've produced a rotating black hole. So how does this work? Well, what we've produced is we have a Kerr black hole hole plus some gravitational radiation. Okay, so that's how we've got away with producing a solution that has angular momentum but is not Kerr. It's Kerr plus some gravitational radiation. So if we take these data and we evolve them, we expect that the gravitational radiation is going to radiate away and that we will be left after some time with just a Kerr black hole. And indeed that's what happens. But in the meantime there's this stuff here, and since we don't want it we will call it junk radiation. If your goal was just to produce this radiation, then it turns out you could actually have just gone and produced Brill waves instead. You don't have to worry about the black hole. Okay. So how does this work? Well, it turns out, so now the total energy in your space-time, right? Right, the total energy in the space-time is the ADM energy, and this will be sort of the mass of the black hole plus some gravitational wave energy. Okay, so the black hole, the solution that we've produced will be a Kerr black hole. Okay, and it will have a Kerr parameter we'll have this Kerr parameter. Well, this is our estimate of the Kerr parameter, right? Now, if we create these data, it turns out that I say, okay, that's great. I can produce anything I want. I get some junk radiation, but that will go away, so I can do what I want. Well, it turns out there's actually a limitation to how high you can make this Kerr parameter. Okay, so if I calculate here J over squared, right? The maximum I can have for my Kerr parameter, of course, is 1, right? That's an extremely spinning black hole. And if I go beyond 1 and I have a naked singularity and nasty things happen and so on, Penrose comes after us. But so we know we can go up to 1. In this setup, right, J is free. We can make J what we want. We can make J 10,000. Okay? But as you make J larger, you will also make the mass larger. Okay? And so you will expect that and by just our understanding of the Kerr black hole, we know that this ratio cannot go any higher than 1. And indeed, it doesn't go higher than 1, but unfortunately, it also doesn't quite make it to 1. So starting at small j, right, if you write a code for this, you of course start with small j to make sure everything's nice. And away you go, and you turn up j, and j over m squared increases, but then it starts to get into trouble and it levels off. And it levels off at about 0.92. Okay, and if you're interested, I can refer you to papers which give you more digits here, but since this is some distance from 1, 92 is probably what we need to know, right? So this is the highest spin you can get, it turns out. Now, it's actually worse than that. Because if we now evolve the data, right, if we evolve the data, some of this radiation, we have this huge amount of junk radiation we produce. As we turn up J, we turn up the mass, J increases, the mass increases, and also this radiation increases. There's more and more of this gravitational radiation. And if we evolve some of it, probably most of it is going to, I mean, you don't know, right? Until you evolve the system, you do not know what's going to happen. to all the radiation. It would be great if it all just left, but some of it will fall in. As it falls, the radiation falls in, the mass of the black hole will increase. If the mass of the black hole increases, J over MBH right? And this is an axisymmetric space-time. Okay, so J is constant. Right? Since it's axisymmetric, there will be no radiation of angular momentum. So the angular momentum will stay the same. So that's something. But the mass will increase, and so this J over M squared will decrease. So once this thing has finally set down, all this pesky radiation has gone away, and you're happy, you will have a Kerr black hole which has even less than this final, than this. Okay, and this is annoying because if we want to simulate astrophysical black holes, we cannot, using this method, we cannot deal with black holes that have spins higher than 0.92. So when people come and tell you, oh, all the black holes in the universe are actually almost extremely spinning, they've got spins of 0.99, what does this mean for us? Well, I don't know, I can't tell you. I don't have data to do that. And there are ways to get around this, all sorts of fancy techniques that have been developed in the last few years, but using this Bowen-York data, you have this limitation. And using conformally flat data in general, you will have this limitation. All right, so you can think of, if you're a masochist, you can think of far more complicated ways to construct binary black hole initial data that are conformally flat, but they'll basically be the same thing, and they'll also have junk radiation. Okay, all right. So enough of this depressing talk. We've done a lot of things. We can know now how to make multiple black holes. We can produce binary black hole data. So now let's look at in the last moments binary black holes. So now we can add two solutions with a momentum constraint. Right, we just make a black hole here, another one here, some distance d apart, and away we go. All right. Now we can produce these momentum constraint solutions. We now have to solve the Hamiltonian constraint. Fortunately, we now can just write this as in this form. We just have a sum of these divergent pieces by R1 if the punctures are at C1 and C2, these are the locations of them, then R1 is actually right, these things are the distances to the two punctures. So you can just do this, and then you can again go and solve the equations. So you can use various methods to do this. If you look at if you want to do this with just a standard relaxation method, Thomas did this in 1998 and looked actually at the properties of these solutions. Yeah? I'm sorry? Sorry, yes. M1 and M2. Very good. Thank you. So he looked at this and looked also at the properties of how to construct circular orbits and so on. If you want to calculate things a little more accurately, you can use multi-grid methods. And this is what Brandon Brugman did. I'll just call them B and B. This is actually 90. Sorry, this wasn't in 98. This was in. What have I got here? Yeah, this was in 2000. That was in 2000. This was in 97. Yeah. Okay. And then you could also be even more fancier, and you could use a spectral method, spectral solver on a compactified domain. Sorry, I'm running out of space here. And this was done by Marcus Ansorg with Bernd Brugmann and Wolfgang Tichy, and this was in 2004. Okay, and what these guys did, and this is what I want to show you some pictures of. So again, this is one of the, to illustrate, going back to this whole problem of question of solving elliptic equations, that this is a 3D problem. You have to make now a 3D grid. You've now got the issue that you're going to end up using a lot of computational resources to go far out to some large radius where you can put a nice Robin outer boundary condition and so on and get nicer solutions. But what you could also do is compactify. Now compactifying is trickier because you have these two punctures there, and that's where most of your numerical resolution is needed. So if someone could leap to my rescue here, I will. Simplest approach, and this is what you should always do first. You should always do the simplest thing first. I think Sasha gave a sermon on this as well, that you always want to do this thing simple first, but once you know what your solution looks like, you know what you're doing, then you can use some more sophisticated methods. And turns out if you use spectral methods work very, very well if you have a very regular solution, a very smooth solution, and then you can capture it with some appropriate basis functions over some small number of points. And so in order to solve this problem efficiently with a spectral method, you basically modify your coordinates so that you well resolve the region where the black holes are. So what I've shown here is what these guys do, this extremely sophisticated and complicated coordinate transformation. If you read this paper, you'll see the particular transformations that are made. And if you read this paper and you have a sufficient amount of aspirin with you, then you can work through these calculations. This is a really, really clever, complicated transformation. I'm going backwards here from the Cartesian coordinates. So this is what everything looks like in Cartesian coordinates, and this is what their mesh looks like. So they have here that they have many, many points around these punctures, and then as you move out further away, the points become further and further apart. This is what this looks like. There is one transformation, so I'm going backwards in terms of the transformation, where this region gets curved up like this. So now you can see that everything starts to look more, the geometry has become weirder, but now the grid is more evenly spaced. You then actually make another transformation that makes these corner points. So now the punctures are actually at the corners of your grid in some new, completely strange coordinates, and the grid looks quite reasonable, except it extends out to infinity. You now compactify that, and you end up with this grid, which now looks completely right. This is just a simple grid in these coordinates. These coordinates are u and v. I don't know, they're something completely strange, and essentially they capture most of the behavior of the solution in a way, right? The coordinates are designed to follow the behavior of the solution, and so now if you solve, you now have functions which are very, very simple on this domain, and so you now can solve this. You can just put now a spectral basis across these directions. The phi direction, I should say, the axis of rotation here is not shown, right? So there's one extra angular direction here, which is it's just left out. So in the final thing, you have these two coordinates in some angular direction, and then you can solve on essentially this number of points. So I think you use about a 30 by 30 grid. Well, 30 by 30 by 10, something like this. So a relatively small grid, and on a small workstation, on this laptop, I could solve fantastically accurate initial data, which then gets unpacked back into these kind of coordinates, and then sent into some huge evolution code that 3D evolution code that runs on a supercomputer. But on this simple tiny grid, I can get the solution accurate enough for the final evolution. And so this is the solution of this function u. Here we have the two black holes are on the x-axis. I mean, you can't see that this is x, but it's x, and they're here and here. And so this function u, has its maxima at the two punctures, and if you zoom in to this region, you can see the solution here. What's shown here, there's a number of lines. What's actually shown is a comparison between this spectral code running at this really cheap resolution, and 3 resolutions of a standard finite difference code, which will run with thousands of points. And it's a convergence test, as always. And as he shows that the poor old finite difference code is very, very slowly converging towards this very accurate solution from this spectral code. So this is just to illustrate in a way that when you go to solve these kinds of problems, your first step is always to do the simple thing and to get a picture of the solution. But then there may be many, many ways that you can more cleverly attack the problem and get a much more accurate solution with less less computational cost. Probably less financial cost too, but of course that will also mean more of your time is involved. But in this sense, this pays off. I mean, this particular method is a code that produces this. Many of the groups in the world who run binary black hole simulations, including all the people that I work with, is who use this solver. This is the way to produce initial data. So spending some time to do it in a nice way can also serve you very well. Okay, so in the last moment, the timing has worked out perfect. How fortunate. I just wanted to provide some references, because I know along the way people keep asking, are there references for these things? And my answer has been yes, but I haven't told you what they are. So I noted down on a piece of paper, which is probably not here. Great, that's all right, I can remember. Some references. Okay, so for all the things that I've talked about, in terms of the numerical methods and so on, one place to go, which you may already be going already for things, is Thomas's book. All right. So there is a section on numerical methods in there, and it talks about, he summarizes briefly, but basically contains all of the essential material that I talked about. There's also, he talks about these maximum, minimum principles, and these things are all pretty much in there. In terms of general numerical methods, in some ways a standard reference is numerical recipes. Right. And this book has been around for decades. There are there's numerical recipes in C, there's numerical recipes in Fortran, there's probably numerical recipes for your iPhone, there's numerical recipes for everything. This is online. You can, often if you go to some university and you get an account on their computer, you'll find numerical, all the recipe, it's all on there. All the code is actually already installed. I think when you go online nowadays, you have to actually sign up somehow or become a member of the numerical recipes club or something. I don't know, but this is a very good reference. And the other thing about this reference is not only is it contains all the basic numerical, it talks all about Runge-Kutta methods, it talks all about elliptic equations, optimization problems, all sorts of things, and also gives you lots of other references, right? So if you then, it's pretty brief in its description, but if you want more information, it tells you where to go. Okay, in terms of numerical methods for initial data for elliptic equations, a very nice reference is a paper by Matt Choptwick and Bill Unruh from, I think, 1995. And it's called, if you look up Choptwick and Unruh for 95, it's called something like multi-grid, an introduction to multi-grid methods in numerical relativity, or something like this. Okay, so that's not the exact title, but it's pretty close, and Google will find it for you. This is a very nice pedagogical treatment of the multi-grid method, which is quite a sophisticated method for solving elliptic equations. It also talks about this successive over-relaxation method that I mentioned very briefly in one lecture, and then it goes through a simple one-dimensional problem to illustrate both methods and how they compare with each other, and then it also goes through the solution of the Hamiltonian constraint for a spinning Bowen-York black hole. And this plot here of the Kerr parameter with respect to J, these things are all in that paper. And so this is actually, if you really want to get in, learn more about doing these things, this is a great paper that you can go and you can essentially work through the examples, and you could reproduce this 2D code and the results that they get. And so that's very useful, I think. In terms of other things to mention. If you, in terms of this, the Schwarzschild things, there's a basically most of the stuff that's in there is, I think I even put it in the notes yesterday, maybe. Let's see if I have this here. Right, there's this paper, Schwarzschild, which is archive. Point. Is that right? 06. There's one digit missing. Oh, that's sneaky. Okay. Well, just a minute. Maybe it's here. Nope. There it is. 0628. Okay. And this is a paper I wrote with actually with Sasha and a bunch of other people some years ago. But this goes through all the details, and we actually got away with this ridiculous title, which is the main achievement, in my opinion. Right. So this way we talk all about this maximal solution, the 1 plus log solution, how you go from one to the other in evolutions, and it goes through this in a lot of detail. So if you're interested in that, you can look at this paper. There's also calculations you can probably work through. I think that's probably sufficient, yeah, in terms of references. Are there any questions, other things that people would like references on? Okay, I think there's a good place. I mean, in particular, if you want to actually work through more complicated examples, this is a very nice. I mean, this is a paper, right? This is, I don't know, 10 pages. You don't have to get some book and work all the way through it. It's just this paper. So that's quite quite a nice place to start. Okay, I think that's.
Okay, this brings us to the end of the last sort of long course in this group. Let's thank Mark for an excellent service. We will have 2 lectures tomorrow in which sort of place these material in a bigger context of astrophysics and gravity.